This is the second video in the stoichiometry unit. This video has two learning targets. We want to be able to determine the limiting reactant in a reaction, and we want to determine the amount of excess reactant or reactants that remain. And here's a list of resources for you, some other videos on Khan Academy. I think there's some good stuff there, and then practice. With this stuff, and really with any of the stoichiometry stuff, just Googling stoichiometry practice or limiting reactants practice would lead you to a wealth of resources. So certainly don't just limit yourself to what you see here. If you want to seek out some of your own practice, please do. Alright, so big key idea for this video. We want to know what a limiting reactant is. So a limiting reactant there's a couple ways of looking at it. It is simply the reactant that runs out first in a reaction. The reactant that runs out first in a reaction. You can also think of it as the reactant that determines the amount of product that can form. And we'll give you examples here of what we mean by each of these. First of all, before we get to an actual example of a reaction, just a scenario that helps us to explain what a limiting reactant is. Let's say you go home after school and you're hungry, so you decide you're going to make yourself a ham sandwich. And you're really hungry, or maybe you have friends coming over and you want to make them all ham sandwiches. And you're just going to go with real basic ham sandwiches. Each sandwich is going to contain 2 slices of bread, and let's say 3 slices of ham. And that's all it's going to be on the sandwich. I know it's pretty plain, but we want to keep this simple. And you go to your cupboard and you get your bread out, and you see that you have 10 slices of bread is what you actually have. 10 slices of bread. And you go to your refrigerator and you see that you have 12 slices of ham. Now, the question is, how many sandwiches can you make? Well, if I'm thinking about the bread, I could make 5 sandwiches because each sandwich has 2 slices, and that would allow me to make 5. But with the ham, I can only make 4 because 4 times 3 is 12. And then once I've made 4 sandwiches, I'm out of ham. And I can't make any more sandwiches. So in this case, the ham is limiting. It is limiting. We're going to run out of ham before we run out of bread. Likewise, it's this amount of ham that determines how many sandwiches we can make. So ham is limiting, meaning it runs out first, which means it determines that 4 sandwiches. No, let's spell the word sandwiches right. That's terrible. Sandwiches can be made. Alright, so that's what a limiting reactant is. Let's see how that applies to an actual problem. So here's our situation. We are told, consider the formation of water, and we're given the balanced equation. We can see 2 moles of hydrogen react with 1 mole of oxygen. You have 2 moles of water. Question: if 4.0 grams of H2 are reacted with 64 grams of O2, which reactant is limiting? So we need to figure out which one's going to run out first. Here is a good way to do that, and in my experience is the easiest way to go about it. What we want to do is we want to convert all the masses of the reactants to moles. Okay, so I'm just going to convert my 4.0 grams of H2. I'm going to convert that to moles. The molar mass of H2 is 2.02 grams per mole. Grams cancel. And I'll do that calculation here in a second. And then I do the same thing with the oxygen. I have 64 grams of O2 and I'm going to convert that into moles. 32.00 grams of O2 for every mole of O2. Okay, so I do those calculations. Let's see, 4 divided by 2.02 to 2 sig figs, that's just 2.0 moles of H2. And then 64 divided by 32, that is also 2. That's 2 moles of O2. Alright, so at this point, what we're going to do is we're just going to create a little chart here. And at the top of the chart is just the balanced equation. So 2 moles of H2 plus 1 mole of O2, that forms 2 moles of H2O. That's the top of the chart. And then what we're going to do is we're going to list the number of moles we have initially. Okay, I standing for initial, and that is the number of moles. Well, I have 2.0 moles of hydrogen. I have 2.0 moles of oxygen. And then because the reaction hasn't occurred yet, I don't have any water. I don't have any water. The next line in the chart is the change. Just call it C. Okay, and again, that's moles. Well, I'm going to approach this in 2 ways. I'm going to first approach it as if hydrogen is the limiting reactant, meaning all the moles of hydrogen will react. So if all the moles of hydrogen will react, that's going to change that concentration by 2 moles, so minus 2.0. For oxygen, it's going to be half of that. And the reason I know that is because the mole ratio of oxygen to hydrogen is 1 to 2. So it will be minus 1/2 times 2. And then for the water, because we're getting rid of the reactants, the water is going to be plus. We're going to add to it. Well, it's going to be the same as the hydrogen because it's a 2 to 2 ratio. However many moles of hydrogen react, 2 moles of water also react. So that will be plus 2.0. And then E means at the end. And notice if I look down the left side here, this spells ICE. ICE. Initial, change, end. Well, 2 minus 2, that's 0. That means all the hydrogen reacted. 2 minus half times 2, well, 1/2 times 2, that's 1. So 2 minus 1, that's 1.0. And then 0 plus 2, that's 2.0. So here, all of the hydrogen reacted. That would be limiting. If I do this the other way around, if I try to get all the oxygen to react, I'm just going to do the same chart down here. I won't write the equation again. But if I do the same thing, I'll just fill in the numbers. We have 2 moles of hydrogen. We have 2 moles of oxygen. We have no moles of water to start with. If I say that all the oxygen reacts, so this is the change, for hydrogen, it's going to be 2 times that. So minus 2 times 2.0. Well, that's not going to work. This can't happen because I don't have that much hydrogen. Because 2 times 2, that's 4. I can't react 4 moles of hydrogen because I only have 2. So right here, this shows us that hydrogen is limiting. It's going to run out first. So, to answer the question, H2 is limiting. H2 is limiting. It will run out first. Question B. What mass of water will be produced? Well, this really is not a whole lot of a calculation to do here. We've already done most of the work for it. Here's why. We just determined up here in question A that hydrogen is limiting. And whenever hydrogen runs out, whenever we end with 0 moles of hydrogen, we have 2 moles of water. So we already know 2 moles of water will be produced. So 2 moles of water produced. Again, we determined that from right up here. That's how much water we're going to get. We get 2 moles of water. So now it's just a mole to gram conversion. We use the molar mass of water, 18.02 grams of water for every mole of water. 2 times 18.02 to 2 sig figs, that's just going to be 36 grams of water. That's what we have produced. All right, question C. I believe there's a question C. Yes. All right, question C. What mass of excess reactant remains? Well, here's what we know. We know that we started with 2 moles of oxygen that we started with. 2 moles that we started with. If we go back to our chart that we made, we can look, and let me put a line here so we can differentiate this. Here's the chart we're looking at right here. If I just look at oxygen, remember excess means there's going to be some left over. I can already see that I have 1 mole of oxygen left over. That's what this tells us. This is what's left at the end of the reaction. I have 1 mole of oxygen left over. So, on second thought here, I didn't really even need to recognize this. I mean, we do know that we started with 2 moles of oxygen. But I know from the chart that 1 mole of O2 remains. Well, if I want to know the mass that remains, I just need to do a mole to gram conversion. Molar mass of oxygen is 32.00 grams of O2 for every mole of O2. Moles cancel. That leaves me with 32 grams of O2. And we've done the problem. Alright, a lot of stuff there that we just saw. In the next example and in the practice, I think when we see the charts, it'll make a little more sense. Seeing it the first time can be a little difficult. Alright, so question 2. We are told to consider this reaction between phosphorus and oxygen. We can see the balanced equation here. And we are told if 25 grams of P4 and 50 grams of O2 are reacted, what mass of P4O10 is produced. This is the same problem we just worked. The difference is we're not specifically asked to find the limiting reactant. However, we still need to determine what it is, because we don't know which of these, the phosphorus or the oxygen, is limiting, so we don't know which one will determine how much of the product, the P4O10, we're going to get. So we're going to do the same thing we did before. We're going to convert the masses of our reactants into moles, so we can determine how many moles. So we need the molar mass of P4, so that is 4 times 30.97, that is 123.88. So 123.88 grams of P4 for every mole of P4. Grams cancel. So 25 divided by 123.88. This gives us 0.202 moles of P4. Okay, now I need to do the same thing for the oxygen. We have 50.0 grams of O2. Converting that to moles. Molar mass of oxygen is 32. Remember, that's O2 because it's diatomic. And now I just need to do a division here. We have 50 divided by 32. And that gives us 1.6. Hold on, I get 3 sig figs here, 50.0, so 1.56. 0.56 moles of O2. Okay, so at this point, we're going to set up a chart. Again, at the top of the chart is simply the balanced equation. We have P4 plus 5O2. That yields P4O10. Then along the left side, I'm just going to write ICE, I-C-E, where I is the initial. And again, this is all number of moles, not masses. It's all number of moles. So I have 0.202 moles of P4. I have 1.56 moles of O2, and I don't have any product to start with because the reaction hasn't occurred yet. Alright, so let's figure out what our limiting reactant is here. So let's say all the P4 reacts. Okay, so all 2.02 moles react, so minus 0.202, not 2.02. The oxygen will be 5 times that amount that will react, because it's 5 moles of O2 for every 1 mole of P4. So this is minus 5 times 0.202. And then for the P4O10, I can see this is going to be the same as the number of moles of P4 because it's a 1-to-1 ratio. So this will be plus 0.202. Okay, so if I do that, 0.202 minus 0.202, that's 0. And then if I do 1.56 minus 5 times 0.202, that leaves me with 0.55 moles of oxygen. And then for the P4O10, 0 plus 0.202 would just be 0.202. This right here shows us that the phosphorus, the P4, is limiting because all of it runs out. I have none left, and I still have oxygen left over. So I don't need to do a second chart because I've already determined what the limiting reactant is. So P4 is limiting. Again, even though we weren't asked to find that specifically, we do need to know what that is. So P4 is limiting. Okay, and then to actually answer the question, what mass of P4O10 is produced? Well, I know we're going to get 0.202 moles produced. I have 0.202 moles of P4O10. Now I just need to convert that into grams. So I'm going to need a molar mass. So 4 times 30.97 plus 10 times 16. That's 283.88. 283.88 grams P4O10 for every mole. P4O10. Moles cancel. And then just doing the calculation, we have 0.202 times 283.88. Get 3 sig figs, so that is 57.3 grams P4O10. Alright, so that is that problem. Next question. What mass of excess reactant remains? Well, if I just go back and look at my chart here, I can see my excess is oxygen, and at the end I have 0.55 moles of oxygen left over after the reaction is completed. So to determine the mass, I just need to convert that into moles. Into grams. I have 0.55 moles of O2. Multiplying by the molar mass of O2, 32.00 grams of O2 for every mole of O2. Moles cancel. So we take 0.55 times 32. That is, let's see, that is just 2 sig figs there to 0.55. So I should probably round that to 18 grams of O2 that are left over. Alright, so last here we have a practice problem with actually 3 questions in it. So I'd pause the video, try this out on your own, and then see how you did. So first question in the practice problem, we're asked to determine the limiting reactant, and we can see the information given to us here. We're given an equation. Notice there aren't any coefficients, so the first thing I would do is I would make sure it's balanced, because as we know, we have to have a balanced equation here. So let's see, I have 1 mole, 1 sodium, 1 sodium. I have, let's see, I have 2 hydrogens. There's 2 hydrogens. There's 1 carbon there, 1 carbon, 3 oxygens. There's 1 and 2 is 3 oxygens, and 1 chlorine on each side. So that is already balanced. Alright, so we have 1.82 grams of HCl. So I want to convert that into moles. 1.82 grams HCl. Converting that into moles. 1.82. Need a molar mass, I guess. 1.01 plus 35.45. Molar mass is 36.46. So 36.46 grams of HCl for every mole of HCl. So 1.82 divided by 36.46. That gives us 0.0499. 0.0499 moles of, left out the L there, of HCl. And then I do the same calculation for the sodium bicarbonate. That's 2.01 grams in a HCO3. And again, I need a molar mass, so that is sodium's 22.99 plus 1.01 plus 12.01 plus 3 times 16, 84 0.01 grams NaHCO3 for every mole of NaHCO3. Grams cancel, and I do the calculation. We have 2.01 divided by 84.01, 0.0239 moles NaHCO3. So I've determined the number of moles of each reactant we have. So now we just need to figure out which is limiting to answer A, and to do that I think it's most beneficial to draw out that chart. So I'll just do that. We'll go down here. I have a little more room to spread it out. It's a little easier to work with. NaHCO3 plus HCl, and that yields NaCl plus H2O plus CO2. So again, I just write the word ice down the left side. Ice standing for, again, initial, change, and end. So I start with NaHCO3. I have 0.0239 moles of that. I have 0.0499 moles of HCl. And I have none of the products to start with because the reaction hasn't occurred yet. Alright, let's say all the NaHCO3 reacts. So that's minus 0.0239 moles of it. Notice it's a 1-to-1 ratio with HCl. So that means 0.0239 moles of HCl will react along with it. And then all of these are also 1-to-1 ratios with the with both the reactants. So these are all plus 0.0239. Plus 0.0239 plus 0.0239. So at the end of the reaction, we're going to have no NaHCO3, no sodium bicarbonate left over. We need to do a quick subtraction here for the HCl, so that's 0.0499 minus 0.0239. So I have 0.0260 is what that should be, because that goes to 4 decimal places, moles of HCl. And then for all of the products, there's 0.0239 moles of product for each of them that are produced, because again they're all 1-to-1 ratio. So to answer question A, determine the limiting reactant, I can see the sodium bicarbonate is going to run out first. There's going to be none left over. There's still going to be HCl that's left. So that means that to answer question A, I'll just write it up here. NaHCO3 is limiting. Alright, question B. What mass of CO2 is produced? Well, if I look down here at the chart, I can see that the 0.0239 moles of CO2 are going to be produced. So I just need to convert that into grams. I have 0.0239 moles of CO2. Converting that into grams, we need a molar mass, so calculate that here. 12.01 plus 2 times 16, that is 44.01 grams CO2 for every mole of CO2. Moles cancel, so 0.0239 times 44.01. Looks like we get 3 sig figs. Slide this over a little bit. That is 1.05 grams of CO2. So to answer this question, 1.05 grams CO2. And then finally, the last question, calculate the mass of the excess reactant that remains. I just go back and look at my chart here. I can see that I have 0.026. That should be 0.0260 moles of HCl left over at the end. So I just need to convert that into grams. The molar mass of HCl is 36.46 grams of HCl for every mole of HCl. 0.026 times 36.46. This gives us, looks like we get 3 sig figs, 0.948 grams of HCl. So just write that here, 0.948 grams HCl. And that is it. Let's see. Just to emphasize some things here that hopefully you picked up on in the working the problems here. We'll go back to the key ideas. I'll jot them down over here. A little space here. So all of these calculations in these charts, okay, all those calculations are based on moles. Okay, it's mole calculations. And the reason why that is, again, we've said this several times in class and in these videos, the balanced equation and how a reaction worked is based on mole ratios. How many moles of each we have, how many moles are going to be produced. So that's why we do all these calculations for moles. So that's why the first step is we convert our masses into moles, then we plug those mole values into these charts, and that's why we do the calculations with moles. And then at the end, if we need to find masses, we just convert the moles back to masses once all is done. So mole calculations, and this is because reactions are based on mole ratios. That's why we do the mole calculations. Alright, that's the end of the video.